Welcome to the final video in the Advent of Code 2022 walkthrough series. So today we're looking at Advent of Code 2022, problem 25. And as is traditional, there is only one part to this problem. Okay, so at the extraction point, there are a lot of hot air balloons drifting down to meet us, and they quickly start unloading all of the equipment that was brought. The fuel heating machine is a new addition, and when this mountain was a volcano, the ambient temperature was more reasonable, but now it's so cold that the fuel won't actually work without being warmed up first. Okay, so to heat up the fuel, the machine Bob needs to know what the total amount of fuel that will be processed ahead of time is so that it can calibrate the flow. The amount is simply the sum of the fuel requirements of each hot air balloon, and the requirements are even listed very clearly on the side of each burner. You assume that the elves will have no trouble, but they come to you because they actually don't recognize the format of the output, and so of course they need your help to decipher them. So this is a list of the fuel requirements, which is listed in some strange format involving numbers 0, 1, and 2, and then a bunch of dashes and equal signs. Okay, so we see that this is a special format, and it's in base 5. So each place value is worth a power of 5 instead of 10. So whereas normally in decimal, the rightmost digit is worth 1, and then the next one is worth 10, and then 100, this time it's worth 1, and then 5, and then 25, etc. And the dashes and equal signs are actually negatives. So normally you're used to only positive digits, so this concept may be a bit weird at first, but it actually works exactly the same way. It's just that the place value is negative when you have a minus sign there. So for example, the symbol 2 equal sign, that the equal sign means -2, so it is -2 times the place value, which is 1, plus 2 times the place value of 5, which would be equal to 8. 2 equal minus 0, 1 would be 1 times 1 plus 0 times 5 plus minus sign, which is -1 times 25, plus -2 times 125 plus 2 times 625. And so that would add up to 976. And so this is called balanced. I guess it would be called balanced base 5. Usually you see balanced ternary, which is similar, but it only uses 1, 0, and -1 in base 3. One of the advantages of balanced ternary is that you actually do not need a sign to represent negative numbers, because you can represent all positive and negative integers purely using the native format. The disadvantage, of course, is that it's really confusing. Okay, so the conversion step is actually fairly easy. Converting from snafu to decimal is very simple, actually. And then the answer is the sum of these snafu numbers, but in snafu format itself. So converting back is going to be the part that's actually a bit more difficult, but it is actually not all that hard either. Today's problem is overall quite simple. So we keep track of a running total, and now we do for line in all of the input lines. Then in order to convert, we essentially need to iterate through the number backwards, incrementing our exponent each time. So what we can do is this: exponent equals 1 initially, or sorry, I guess coefficient equals 1 initially. And now we can say for x in the inverse of the line, and then at the end of the loop, we will multiply the coefficient by 5. And now we could convert each snafu number individually and just do like k equals 0, and then do like k plus equals equal dash 012 dot find x. So that would convert it into the place value from 0 to 4. So we subtract 2 to make it go from -2 to +2. And then just multiply that by the coefficient. And at the end, we can just do total plus equals k. So this will convert each number into the actual numeric format first, and then add it to k. But we can simplify this a bit by just increasing the total itself, like so. And so this will get us the sum. And as a sanity check, we should output this value first, just to make sure that we are getting 4,890. Now we need to convert it into snafu format. So this is actually also not that bad. So to convert it into regular base 5, what we would do is this. So we start the output as the empty string, and then while total is not equal to 0, we will essentially process it from the back. So if you want to convert a number into regular base 5, think about how you would convert a number into decimal, assuming you just had some arbitrary count. You know that the last digit has to be the remainder when dividing by 10, because when you divide by 10, you essentially shift all the digits over to the right, and so the last digit is the remainder. And so output would equal the remainder plus, and we tack that onto the, sorry, no, that's wrong, right? It should be at the end. No, it should be at the beginning because we're building from the backwards. And so each time we'll add the next digit forward because we're moving from right to left. And then we could just do total floor divide by 5. We essentially shift it over all of the digits. And so this is how we would convert into regular base 5. Oh yeah, this needs to be a string. So that's regular base 5. And we can verify that this works by converting it back into decimal. So 0 times 1 plus 3 times 5 plus 0 times 25 plus 4 times 125 plus 2 times 625 plus 1 times 3125 is equal to our original number 4,890. So now, how do we convert this into SNAFU format? Well, if we can say, we can let remainder equal total mod 5, and then we can also do total divide equals 5 first. If the remainder is less than or equal to 2, so in other words it's 0, 1, or 2, then we just convert it using the normal format. And so if we were to have a number where all of the regular base 5 digits would be 0, 1, or 2, then converting it into SNAFU would actually be the exact same. It's when the remainder is 3 or 4 that we need to do something differently. And it turns out that it's actually not all that hard. Remember how 8 was converted into 2 equal sign? Normally it would be converted into 1, 3. And so what we do is we essentially add 5 to our number and then subtract it from the decimal after. Or compensate for afterwards. So, or sorry, no, it's the other way around. We essentially subtract 5 and then compensate for afterwards. So 1, 3, because 3 is an invalid digit, we subtract 5 from our number, which gives us 1 equal sign. That would be 8 minus 5. And so we add the 5 back, but we can't do it within our current digit. We add it to the next digit before us. So essentially we take our 1 equal sign and then bump it up to 2 equal sign. So we take the 1, 3, we turn the 3 into an equal sign, which subtracts 5, and then we advance the digit before it, which adds 5. And by the way, this is how the conversion process for balanced ternary works as well. And you could theoretically do this for any base that's been shifted into the negatives partially. Okay. And so now, otherwise, we do output equals, so we want to convert 3 into 0, 1, 2, 3 into equal sign and 4 into minus sign. Like so. And then we just do total plus equals 1. Because we've divided total by 5, and then when we add 1, we're essentially adding 5 to the original number. And so this would bump up the next place value, and that would possibly get cycled around to the negatives as well. And so we see that this now gives us our correct puzzle output. So the difficult part of this is really just thinking up the converting back into SNAFU process. This part is relatively simple if you already know how to do base conversion, because you're really not actually changing anything. You're just allowing for negative numbers, which were never really explicitly disallowed in the first place. It's this process that's a bit more difficult to wrap your head around, but essentially the core logic behind it is if our rightmost digit goes out of range, then we just subtract 5 and add it onto the next one, which, to be clear, is more or less how regular base conversion works anyway. Let's say we have the number 21. You could write that as 1 in the tens digit and then 11 in the in the ones digit. But 11 is too large, it's out of range, so we subtract 10 and add 1 to the digit before it. This is exactly the same. It just feels a bit strange because we're working with negative digits. But really the core logic is the same as always. Okay, and as always, once you've solved all of the previous 49 problems, Part 2, you just click the link here, start the Blender again, and it'll show you the final page once you've reached all 50 stars. And thus, the Advent of Code 2022 walkthrough series comes to its conclusion. I hope you enjoyed this series. If you enjoyed watching my content, please like and subscribe. I would greatly appreciate the support. And I'll likely keep posting educational content on my channel. If you haven't already, I posted a poll on my community tab, which you can check in my channel, basically just asking what sort of content everyone would like to see moving forward, since AOC won't be here until the next year. And so, given the feedback that I've received there, I'll probably continue showcasing some cool problem-solving techniques and also going through some specific topical videos, such as the modular arithmetic one. I know a lot of people requested a graph theory one, so that's what I have in mind next, but I'll keep thinking of new things to post on the channel as time goes on. Anyway, thank you so much for watching. I hope you enjoyed and learned something, and I'll see you sometime again.